Welcome, guys. Okay, so this video, let's talk about central limit theorem. So this theorem is famous in the probability theory or the large number theory. Okay, so probability is the most important theorem. Like maybe you hear it already in high school or something. Okay, so but I think seldom people talk about proof. Right. So I give the short proof. Okay. Okay. So if x1, x2 up to xn is a random variable driven by population over mu and the finite variance, or basically you can think that this x1, x2, and xn are the IID distributions, or identical and independent distribution, and they have the mean mu and the variance sigma. And then let's say you take their mean, right? So you just sum of them divided by n and minus mu divided by sigma and take a square root of n. And then you take the n goes to infinity. Then z will become the standard normal distribution. So this theorem, the beautiful for this theorem is that no matter how many or what the distribution is, if the variance is non-zero, then if you add them up and take the suitable combination, and as n grows to infinity, then always become a standard normal distribution. So this is the general rules for all the probability distribution. Okay, to prove this, let's make a simple assumption. So without loss of generosity, right, I can make the mean to be 0 and the variance to be 1. Okay, this is easy. You can check this easily, right? Because I can always shift and divide by sigma. So I can just make a mu to be 0, sigma squared to be 1. So it means that each exi 0 and the ex1 squared is 1. Okay, and the z now become this. Okay. So the theorem says that if n goes to infinity, then Zn will becomes the normal distribution of the mean 0 and the variance 1. Okay, I also add the assumption that each for this random variable for this probability distribution, it has the moment generating function. Okay, this is the usual assumption that moment generating function exists for this probability distribution. Okay, so once I add this assumption, the proof will be very simple, right? Because now we can take the moment generating function of this Zn, so become mx divided by square root of nt I from 1 to n. Okay, so this is because this is independent, right? So the linear, the moment generating function will be product of all the linear, each component. Okay. So mgnt will be mx square root of n to the power n. So it's mxt divided by square root of n to the power n. Right. So by your calculus, you know that this is 1 plus the exponential x t divided by square root of n, and exponential x squared t squared divided by 2n, and plus some arrow term, call it en. Okay. So we know that ex is 0, ex squared is 1, right, by our assumption. So that means it's 1 plus t squared divided by 2n plus arrow term to the power n. Okay, so by definition, by the Taylor expansion, we know that en goes to 0 as t divided by square root of n goes to 0, right? But if we fix t and we let n goes to 0, then we have when as n goes to 0, then en goes to 0, right? So if we fix t, then this is the expression. So when n is very large, then this moment generating function of Zn becomes limit n goes to infinity. We can cancel this term. We can ignore this term, so it becomes 1 plus t squared divided by 2n to the power n, right? So by the definition for a natural constant, this is exponential t squared divided by 2. Okay. So that means the moment generating function now is exponential t squared divided by 2. So compared to the usual normal distribution with n mu and sigma squared, this is the exponential mu t plus a half sigma squared t squared. So right, so compare these two. Compares to, right? We know that this is exactly the normal distribution for the mean 0 and the sigma squared equals to 1. Okay, so this proves that we need another lemma that if you have a two probability distribution and they have the same moment generating function for all t, and then they will be the same probability distribution. To prove this, you may need some real analysis or some further very technical assumption. So we will not talk about this, right? But this proof is like the maybe 99%, 99.9% very accurate proof. Okay, so this is the proof idea of the central limit theorem. Okay, and I will see you guys in the next video. Be sure to subscribe to my channel. Thanks.